Last speaker for this morning is Ziska, who is a research plant physiologist coming to us from the USDA Agricultural Research, what does the S stand for? Station. So Lou's going to talk today about invasive climate change and CO2 and the rest of the story.
I am going to talk about that, but I'm also going to do something a little bit differently. I'm going to try and do an experiment in the next 30 minutes, and I'm going to need your help. So let me give you a little bit of background. You'll notice on the bottom of the slide it says Crop Systems and Global Change Laboratory. We are no longer the Crop Systems and Global Change. Global Change is taken out of our name. We are now the Adaptive Crop Systems Laboratory. Woohoo! Okay. So one of the things that was clear in the breakout communication session yesterday is that we are going to have to overcome that skepticism when it comes to climate change. So my assistance that I need from you is that I need you as an audience to be climate change skeptics. Okay? So can we all practice the climate change skeptic attitude? All right, so keep that in mind, all right? And my goal, my challenge in the next 30 minutes, well, actually the next 4 years, is to, in as simple and as direct a way as possible, convince you of the reality of global change and CO2 and invasive species biology. So I want you to maintain that skepticism. I'm going to be as simpatico as I possibly can in the next 29 minutes to try and reach you in that regard. So with that in mind, I want to begin with looking at atmospheric CO2. When you take a fossil fuel, you have a lot of carbon. And when you burn that to produce energy, which is the cornerstone of our economy, you have to oxidize it. You know that oxygen is needed for fire to occur. When you take oxygen and when you take carbon and put them together, one of the byproducts is carbon dioxide. So that byproduct comes from primarily from fossil fuels and cement, and about 10% of it comes from burning of forests. Where does it go? Well, about 25% of it stays in the forests and the plants. About 25% of it is dissolved into the oceans, and about 50% of it stays in the air. Now, how do we know this? Well, we've been monitoring carbon dioxide at Mauna Loa, Hawaii since the late 1950s. Now, I thought at first this was a liberal scientist's dream, because if you go to Hawaii, I thought maybe they were there for the Mai Tais or the nice beaches. It turns out that Hawaii is the most geographically isolated spot on Earth. And by taking the CO2 samples at 10,000 feet, they're doing this away from where people are, from where industry is. So this is their idea of coming up with a background CO2. And as you can see, since the late 1950s, the amount of carbon dioxide has increased by about 30%. And we all agree on that, whether you're a skeptic or a non-skeptic. These measurements have been repeated by other monitoring stations since this initial time. So if you go into the future and you go into the models, and I don't want to get hung up on the models, they all predict a range of things. But for right now, we're sort of following along that red line. And so if we follow that red line, we expect to see around 800 parts per million by the end of this century. Okay, so 800 parts per million carbon dioxide. So as the carbon dioxide goes up, the big question is, so what? Who cares? Parts per million. I mean, really, seriously, parts per million. What possible difference would that make? Well, to explain that, let me look a little bit at what's in the atmosphere. Mostly it's nitrogen and oxygen and argon, right? But there are a couple of really special gases that are referred to as global warming gases, right? They're very different. How do I explain global warming gases? Let's see. Let's turn to the guitar. How many of you in the audience have ever played a stringed instrument before? Can I see a show of hands? Oh, excellent. I love it. So my question is to you, the climate change skeptic. If I tune 2 strings of my guitar to the same frequency, let's say A, which is 440 hertz. I tune 2 strings to the same frequency, and I pluck 1 string. What will the string next to it do? Sorry?
It'll vibrate.
It'll vibrate. What if I'm a liberal? Will it still vibrate? Is that yes?
Yeah.
Okay. What if I'm a Methodist? Will it still vibrate?
Yeah.
Are you telling me that the laws of physics are independent of party or religion, religious domination? Really? I hope nobody tells Ted Cruz this. This would be quite a shock to his system. You're quite right. Of course, the guitar strings will vibrate. Now, what does this have to do with global warming gases? Well, it turns out that global warming gases, like water and carbon dioxide, also resonate. They don't resonate in the key of A, but they resonate in the key of infrared, or heat. So whenever heat passes one of these molecules, they vibrate, right? They absorb some of that energy that would otherwise be lost. And we've known about this for quite some time. We understand that there is, in fact, a natural greenhouse effect. And that's what keeps you warm. If there was no CO2 or water vapor in the air, the average temperature would be minus 18 degrees Celsius. The fact that you're not all huddled around a fire in a fur coat is due to these greenhouse gases. This is a good thing. Of course, if you add more of them, it's going to get warmer, right? But the way it gets warmer is important. And the way it gets warmer is dependent on the relationship between those 2 gases. Now let's ask the question first. Where is it warm and wet? Where is water vapor the dominant greenhouse gas, global warming gas? Well, on the Earth, that would be around the equator, where it's nice and warm and humid, right? Now there, the rate of warming as CO2 rises is less. Now let's reverse that for a moment. Where is the air dry? Doesn't hold a lot of water vapor, and therefore adding CO2 will have a bigger effect on surface temperature warming. The poles. We see faster rates of warming at the poles. Where else? Where else is the air dry? The deserts. So we see faster warming in the deserts. We see, in fact, as you go up in altitude, that the air becomes drier. It's a factor contributing to glacial melt. We see that even seasonally. In Massachusetts, for example, in the winter, the air is dry. During the summer, it's warm and wet. So we expect a bigger temperature increase in the winter as opposed to the summer. So if you can remember that water vapor can be a dominant warming gas with little effect of CO2, but when the water vapor is low, adding CO2 will increase the surface temperature. Now, if I have a globe where some places are warming very quickly and other places are not warming quite so much, what's that going to do to extreme events? Is that going to increase it or decrease it? Increase it. Do you understand the basic physics now of climate change, of global warming? Excellent. That's the first reason why you should care about the increase in CO2. Let me give you the second reason. Well, I'll skip all this about plant biology consequences. Let's go to a second reason, because of course there has to be a silver lining in this, right? You know, based from high school, from junior high even, that plants need light, they need water, they need nutrients, and 95% of them, those with the C3 photosynthetic pathway, need CO2. So adding more CO2 is plant food. This is what Lamar Smith, head of the Science Committee in Congress, says. And in fact, the rapid increase in the atmospheric CO2 is going to alter all of global change biology. And I don't know if you downloaded this yesterday from the same website. I got this from the ExxonMobil website. And you can see for loblolly pine, which is a major source of wood in the southeastern United States, that when you add more CO2, it grows more. Yay! Of course, when trees grow more, the wood is, a little less dense, so it's not so strong. So, the wood may be a little bit weaker. And, when you give the plant more CO2, you affect the chemistry of the plant so that its defensive compounds can be a little bit less, and so it might be a little more vulnerable to more insect pests. And of course, CO2, unfortunately, is not a very smart molecule. It also makes weeds grow more, like kudzu. And so, weeds are, I'm sorry, did I say weeds? I'm sorry, there's a new directive. We don't call them weeds, they're alternative crops. So you have all these issues for plant biology. I'll skip all that. Let me look for a moment now on invasive plant species. And those are defined as a alternative crop species, usually non-native for a given region, whose introduction results in widespread environmental their species degradation. But there's a cost to this. There's a cost to the United States of America. You have to pay more money in your taxes. You're losing jobs as a result of these invasive species. They must be stopped, right? Now I know that some of your tree huggers out there are going, well, it reduces habitats and reduces diversity, but as a hunter and a fisherman, it also affects where I can hunt and what I can fish, which also affects, gets me kind of irritated. But the more irritating thing is the amount of money that we lose as a country. So I want to try and, if I can, give you some examples of how climate change and rising CO2 levels are going to impact invasive species biology. And I'm going to begin with CO2 and cheatgrass, Bromus tectorum. Now, cheatgrass, what it does is it comes into an area where there's native western vegetation, and it changes the ground in such a way that the number of fires goes up. So the native vegetation, which can take a fire, say, every 50 years, now has to deal with this new invasive, which has changed the fire frequency to every 5 years, and as a result of that, it becomes all one big monoculture of cheatgrass. All right? So the question we had is, how will the changes, I'm not talking models, I'm not talking what's going to happen at the end of the century. How has the recent change in CO2 affected cheatgrass biology? And specifically, we looked at cheatgrass from 3 different populations from differing elevations within the Sierra Nevada range. And we looked at the recent small changes in CO2 to see whether or not that was affecting cheatgrass growth, because the growth, of course, is a factor in terms of fireable material, and whether or not CO2 could be a factor in fire frequency. So basically, here are the 3 different cheatgrass biotypes. And what the x-axis is showing is the above ground biomass, grams per plant, and the CO2, the 4 CO2 concentrations of 270, which is pre-industrial, 310, which is the beginning of the monoloic curve, 370 or so, which is when we did the experiment, and around 410 or so, which is the current CO2. And what we found is that when we actually harvested and weighed the plants at the different times, one at about 60 days after sowing and one at about 90 days after sowing, is that for all of the different ecotypes, we found that they did in fact respond to CO2. CO2 is plant food, yay! Oh wait, no, not in this case. So what it shows, essentially, is that recent CO2 increases may have affected the biomass of cheatgrass, and the biomass in turn is related to the fuel load, that is, its ability to start fires. Wait, there's more. It turns out that it also can result in cheatgrass producing more seed. so that it can establish itself a little bit faster. And interestingly enough, when you look at the potassium concentration, more CO2 causes the potassium concentration of cheatgrass to go down. And the relationship between the heat released when you burn a gram of cheatgrass and the potassium concentration is inversely related. So the more potassium you have, the less heat is released. If CO2 reduces the potassium concentration, it means that more heat will be released per gram of cheatgrass that's burned. So overall, these recent changes are associated with growth rate and biomass production. There's some indication that that in turn is going to suggest a faster time to when a cheatgrass monoculture will reach the fuel threshold needed to sustain fire and greater fire frequency. And CO2-induced decreases in mineral composition may increase combustibility, but it's still early days. There's additional data that's needed on this. Did I mention that cheatgrass occupies 60 million acres in the West? Did I mention that the fire frequency in the West is going up? Wouldn't it be really interesting to understand the role of rising CO2 on cheatgrass biology in respect to looking at climate models that are associated with the outbreak of wildfires in the West? So, ignition probabilities, a lot of very fancy science words, but basically, we think there's a link. We'd like to find out more. Kudzu, one of my favorite all-time weeds, and warming temperature. Kudzu is referred to the vine that ate the South, the Confederacy's revenge, a vegetative form of cancer. There are all kinds of different epithets for kudzu. Let's look now not at the CO2 aspect, but let's look at the temperature aspect. There was a USDA scientist named Clyde Reed who in the late 1960s published The Common Weeds of the United States. And at that time, that line that's shown there was the northern limit of kudzu. Now you notice in here, even though kudzu does occur on the East Coast, I haven't included it. And there's a couple of reasons why. One is there are urban populations on the East Coast. Urban areas tend to be heat sinks, and that has an influence on what gets established. In fact, I think for some of you who are maybe interested, not as climate change skeptics that you would be, but if you were interested in looking at invasive species biology, I think you'd find that urban areas with their higher heat sinks may in fact be a very strong repository of climate change species. Just saying, just saying. And we wanted to get away from mountains so that we could look just at what's happening in the Midwest with kudzu. And our question was, are warmer winters, because remember, the relationship between CO2 and water vapor means that winters are going to warm faster than summers. Are winters contributing to the northward migration of kudzu? This is work done by Bethany Bradley, who is a student at the University of Toronto. We know that kudzu has been introduced into the US at various times, and we know that at the northern limit, its asexual reproduction is important. So what she did is to take these different populations and to expose them to different temperatures for a few hours. And she looked at the relative conductivity, the RC. All she did was grow the tissue at a certain temperature, apply an electrical charge to it. If the electrical charge showed a strong conductivity, that is a relative conductivity of 1, then all the cells in that piece of tissue had basically broken open and it was dead. If the conductivity is low, then the tissue is still intact. Okay, fairly straightforward. But basically, regardless of the population, if that kudzu was exposed to 1 day of -28 degrees, it died, regardless of where it was from. So we use that as our sort of cutting off point. Has the minimum temperature threshold changed, particularly for areas within the Midwest? So we looked at data from southeastern Nebraska, Missouri, Illinois, Indiana, Pennsylvania, from about early 1970s onward. This solid line is the -28 degrees line, that's the limit threshold line, and this is the 95% interval. So as you can see, for all of this, In fact, these temperatures have now risen for much of the Midwest to a winter temperature that is above that which will kill kudzu. And kudzu, as of 2006, this was now the northern line, this dashed line here. Doesn't mean this is all solid kudzu between here, but this shows that this is where kudzu is being reported. Let's move to the future. Let's look at the 45-degree line, latitude line, halfway between the North Pole and the equator. And let's look at what's happening there. Minnesota, Wisconsin, Ontario, Canada, Michigan. And this was the data at that time in 2006. You can see again, the minimum temperatures are rising. This is the minus 28-degree temperature. And we used a very simplistic model. Where would this line be when there's a 95% confidence that kudzu will be able to grow? So this is a date at which there is less than a 5% chance of the location is experiencing a temperature below the minus 28 degrees threshold. 2022 in Minnesota, 2019 in Wisconsin, 2015 in Michigan, 2021 in Southern Ontario. And now, thanks to the genius of EDD maps, and Chuck Barjan, could you stand up or wave, stand, whatever. Thank you so much from the University of Georgia for doing this, because this is, you can't imagine what a resource that bugwood is. So that's the northern range of kudzu as of 2011. You can see now it's moved forward. This is the dashed line. And from EDD maps, each of the green dots is a county that's experienced at least one report of kudzu. Anybody from Benzie County in the room from Michigan? Really? Excellent. There's cash involved. See me later. So this is, in fact, as of 2015, the first report of kudzu in Michigan. I looked at the 2017 map just before I came. There was one report of it in 2015. There are now 4 reports of it, and there are 4 counties in south central Michigan that are now reporting kudzu. So the reason, another reason we care about kudzu is that the US leads the world in soybean production. Which of these leaves is soybean and which of them is kudzu? Both are hosts for Asian soybean rust, which could devastate the economic status of soybean production in the US. So where kudzu goes isn't just a question of aesthetics, it's also a question of dollars and cents. So as winter temperatures warm, kudzu appears to be expanding. I would suggest that it's likely that other pests, weeds, insects, diseases, some of which we've already been presented with, are also moving. There's another aspect of this that hasn't received a lot of attention, and it's an important one. We look at macroscopically things we can see, and yet I would argue that pathogens, diseases that are unique to agriculture, such as avian influenza, can also change. Maybe some of you remember a couple of years ago when the price of eggs, a dozen eggs, went from $2.75 to $6 for a dozen. The reason for that was there was an outbreak of a new strain of avian influenza in the middle part of the country. It caused millions of dollars damage. We still have no idea where it came from. We need to keep track not only of the big things, but we need to keep track of the small things as well. And of course, being skeptics, my first reaction would be, so what? Hey, I'm gonna go to the grocery. I know Home Depot. I'm gonna get some Roundup, right? I'm gonna get some Roundup and I'm gonna take care of my weeds. It's not gonna be a problem. Of course, that does assume right? That the rise in CO2 and the rise in temperature don't alter the effectiveness of what you spray, do they? Well, we spray a lot of Roundup. This is from USGS. I think the dark lines are about 90 pounds per acre, something like that. And you can look at this and you can pretty much tell where the breadbasket of America is. So we use annually about 180 million pounds of Roundup. Now, you can understand that. In fairness, if I'm farming, if the average farm size in the US is between 400 and 500 acres, you ain't gonna pull your weeds out by hand. You're gonna use a chemical means to control them, right? Understood. So, wait, what does CO2 do to chemical management? And this is some work we did with Canada thistle. I should explain, by the way, it's called Canada thistle in part because General Burgoyne, during the Revolutionary War, when our brave US soldiers stood up against the British, Burgoyne invaded down Lake Champlain and he bought hay for his horses. And part of the contamination of that hay was this Canada thistle. But of course, if you lived in Vermont or New Hampshire at the time, you thought it was biological warfare because this is such a noxious weed. And one of the first laws passed when Vermont became a state in 1790 was a law outlawing Canada thistle. If it makes you feel any better as conservatives, in Australia, they refer to the same plant species as California thistle. So what we did here is on the left, we sprayed with the recommended dosage, and we got pretty good control. On the right, the Canada thistle grown at 700 parts per million, we got zero control. Why? What's going on? Well, it turns out that if CO2 is plant food, it doesn't make each part of the plant the same. In this case, for Canada thistle, it made the roots grow more than the shoots. And as a result of that, this is to give you some idea of what Canada thistle looks like, the roots are capable of re-sprouting, okay? So if I don't kill all the root, the plant will come back. And so what we think happened is that at the current level of recommended dosage, it was not enough to kill the root. And basically the plant just came back. Now, can you increase the dosage? Can you increase the concentration? Of course you can. Of course, it costs money, too, to do that, right? If you're a farmer, you have to pay the extra cost. So what are the implications of all of this for pest management? I think the first implication is monitor. All of you are patriotic Americans. You understand that during the 1960s and the 1970s, we waged a Cold War with Russia. It was up to us to keep track of those weapons of mass destruction before they did damage to the United States. You know, like pine bark beetle, right? Which has destroyed over 35 million acres. Now, Chuck's work has been outstanding in this regard, and with respect to the United States. And individual countries, in fact, are starting these kinds of programs where they keep track of invasives within their country. But I wish that in the context of global climate change, we had global monitoring. Wouldn't that be wonderful? I mean, if only we had, I don't know, some kind of handheld computer device that 3/4 of the world's population used. And it took pictures. And it could take pictures of invasives. And you could share those pictures with a major agency of emerald ash borer. And it would be a global thing. And some major corporation could make tons of money by advertising their products and yet at the same time keeping track and monitoring where all these invasive species were going in real time. I know, science fiction, I know. That's never gonna happen, right? I mean, you know, it's not like we would be motivated to do something like that in the near future. Oh, well. The second part is, in addition to monitoring, is mitigating. because one of the major and most effective strategies is what we call EDR, early detection rapid response. I'm sorry to pick on you, Chuck. Can you tell me what that seedling is? Pardon? No? Can anyone tell me?
Is it kudzu?
It's kudzu. It's this plant. Now, I know this will come as a shock, but it turns out that it's much easier to manage kudzu when it's in that condition, an early detection, than when it gets to this point, right? So mitigation of keeping track, monitoring is important, but mitigation of what comes in early on has to be a part of that management. And finally, we need more management options. It used to be when I was in grad school that we talked about integrated pest management. And then a Monsanto representative came to our college and they said, oh, Roundup. Roundup will kill 99% of everything. And it's so effective that it will never be, there will never be a gene that will be found that will cause Roundup resistance, ever, ever, ever. Honest, she said that. And so everything switched for 20 years where nobody studied integrated pest management anymore. We just sprayed with Roundup. We need to go back to the basics. And as part of that, we need to include a better assessment of what tools are available, when should we use them, what are the physical options, what are the biological options, what are the cultural options. Pesticides should not be the first thing, but should be the last thing. I know you're close to stop.
Oh, we're at stop.
We're at stop, okay. Never mind. And this is my last slide, monitor, mitigate, manage. Proactive is better than reactive, many tools in the toolbox. And you guys, the skeptics, what do you think about this? How can we make America better? How can we make the economy better? How can we keep these foreign invaders from coming into our shores? Okay? How do we do that? What ideas do you have? Bring them to the table. Okay? All right. I'm overdone. So thank you all very much.